So welcome everyone. Today we are very happy to have Dabson from University of Chicago, and he's going to tell us about bosonization of Fermi surfaces and co-adjoint orbits. Over to you, Dab.
Okay, yeah, thank you very much. My great pleasure to give a talk at the AFFR after so many years. I'm going to tell you about bosonization of Fermi surfaces and co-adjoint orbit. And the plan of my talk is first to remind the audience about Landau's Fermi liquid theory, and then mention one peculiar aspect of Landau Fermi liquid theory that is valid at zero temperature. That is, it describes the dynamics of the shape of the Fermi surface in the sense that I'm going to describe. And I'm going to tell you why the method of the co-adjoint orbit is an ideal method to reformulate Landau Fermi liquid theory as a field theory. In particular, the relevant group is the group of canonical transformation. We are going to review the group of canonical transformations and its co-adjoint orbit and describe how the Fermi liquid can be formulated as a dynamic on a co-adjoint orbit. And then at the end, I'm going to present to you the action principle that give rise to Landau's Fermi liquid theory. If there is any question during my talk, please interrupt me at any time. The work that I'm going to be described is done some time ago with my collaborator Luca Della Cretas, who is now assistant professor in Chicago, Ishian Du, who is a student in Chicago, and Umang Mehta, who is now a postdoc at Colorado, but he was a student at Chicago at the time we wrote this paper. The paper that I'm going to describe is this one, but a lot of details with better presentation is given in Umang's PhD thesis that you can also look up on the archive. So let's go back to history, to the beginning of solid-state physics, which can be dated to 1928, when Sommerfeld formulated the what is now called Sommerfeld's model of matter. In this model, a metal is viewed as an ideal gas of electron, since electrons are fermions, and the temperature of a metal is rather low compared to the Fermi energy of the electron gas. We have a degenerate gas. In 1928, Sommerfeld has an idea of applying quantum mechanics and Pauli exclusion principle to the electron gas. So in this model, the electrons, we have like free fermions, and this gives rise to various predictions. One prediction is the contribution of the electron to the specific heat of a metal, which is a linear function of temperature. Another prediction that to derive which one need to make some assumption, but reasonable assumptions about the dissipation mechanism, impurities, and how electrons scatter on impurities. But with these assumptions, one can derive the so-called Wiedemann-Franz law, which says that the ratio of the thermal conductivity over the electrical conductivity, kappa over sigma, is a combination of fundamental constants, the Boltzmann constant in the charge of the electron. And this law seems to hold very well, at least within the class of simple metals. So this is a very simple model which has many interesting and experimentally verifiable consequences. And right away, a question arises: how comes that this model works? Such a simple model where electrons is viewed as free fermion. free particles. And the puzzle here is the following. In a typical metal, the potential energy of interaction between the between the electron, which is E squared over R, where R is the typical distance between the electrons, is of the same order of magnitude as the kinetic energy between the electrons. And this kinetic energy is h bar divided by m e h bar squared divided by m e r squared. You see here the typical momentum of the electron is h bar over r, and the kinetic energy is p squared over m, which is h bar squared over m e r squared. This condition is true in metal, and you can see this simply reduces to the statement that the typical distance between the electrons is of the same order of magnitude as the Bohr radius, and that is true in metal. These two energy scales are of the same order of magnitude as each other, which invalidate the assumptions of the Sommerfeld model, which is that the electrons behave as a free electron gas. Why this picture works so well? The answer to this question was given by Landau in a couple of papers written around 1956, 1957. And he made observations that if we are interested in the physics at low energies in his words at temperature which are low in comparison with the temperature of degeneration, that is T much less than the Fermi energy, then he said that one can show that the quasi-particle is almost stable. That is, the interaction between the particle becomes smaller and smaller as the temperature goes to zero. So we don't need to assume that at the microscopic level, electrons are weakly coupled. All we need to do is to go to the physics of small momenta, small energies, and then we would have a system of particles that should interact with each other weakly. Landau's Fermi liquid theory is now the basis for our understanding of many systems in nature, including helium-3 liquid, electrons in metals, neutrons in neutron stars, maybe quarks in quark matter, if such exists in the core of neutron stars, and possibly many other systems. It's also a basis for the construction of other states of matter. For example, the superconducting state is constructed by pairing the electronic quasi-particle in Landau Fermi liquid theory. One of the system that we would like to understand, but people still don't completely understand, is the so-called non-Fermi liquid, which should be viewed, one way to view it is a system where we start with a Fermi surface, like a Fermi liquid, and then couple it to a U1 gauge field or a massless bosons. This system, which we call non-Fermi liquid, despite much effort, is still not very well understood. And one reason I will describe, I would argue that the main reason from the point of view of field theories that this is a difficult problem is that Fermi liquid is a very unusual phase of matter. It is a phase with too many degrees of freedom. Maybe I will tell you in what does it mean. The specific heat of a Fermi liquid behaves like T, while in D dimension, the specific heat of, say, conformal field theory behaves like T to the power of D minus 2 or D minus 1, where D is the number of space-time dimension. If one defines the number of degrees of freedom, the number of fields, in some sense, the number of fields to be CV divided by T to the power of 1 minus D, 1 minus 1, which would be a rough measure of the number of fields in the infrared. That number goes to infinity if a T goes to 0, if D is larger or equal to 3. If we have a system in 2 plus 1 dimension and higher, the Fermi liquid is a state with many more degrees of freedom than the typical quantum field theory. Now, the non-Fermi liquids have been argued to be relevant for several experimentally realizable systems. So here, these systems typically has a phase diagram like what you see here on the left. One particular very well-known example is cuprate. Cuprate have a superconducting phase, and above the in the region above the superconducting temperature, one has signals that the theory describing it cannot be the Fermi liquid theory. And one of the experimental observation is the linear dependence of the resistivity on temperature. The resistivity of a Fermi liquid should behave quadratically as a function of temperature, while in this class of material and many other classes of materials, the dependence seems to be linear. We do not completely, at least I am not sure. It's unknown to me how strong the evidence that behind this physics is the physics of a non-Fermi liquid. But there is one particular system where I'm almost sure that the low energy physics should be described by a non-Fermi liquid. That is a system of a half-field Landau level. So half-field Landau level of electrons with short-range interaction is a non-Fermi liquid of the so-called composite fermion. I will not explain this now, but if there is any question, I can tell you later why it is so.
So sorry, Dam. Thanks for this beautiful introduction. Just to check, the reason why we expect for a Fermi liquid that rho will go like T square is the same reason Landau said in his paper, that the collision probability goes like T to some power because of phase space suppression. Is that correct?
Yes,
or?
that
Okay.
exactly.
Okay.
Yeah.
Okay, thank you so much.
So here, if you apply the same logic, you would expect that for this quasi-particle, the lifetime scaled like temperature. So the energy scale like temperature and lifetime scale like temperature, and the ratio of lifetime, ratio of the decay width over the imaginary part and over the real part of the energy is constant, doesn't goes to zero as energy goes to zero. So that's the signal that we have no quasi-particle at all.
Okay, thank you so much.
You're welcome. Landau's Fermi liquid theory is often described, at least in the literature, the more modern literature, as a theory of free Landau quasi-particles. However, as I will tell you, the structure of the theory, at least the structure of the theory formulated by Landau, is very different from free field theory. It is actually instructive to learn how Landau described his creation, the Landau's Fermi liquid theory. I think it is the theory doing that, we would see aspects of the theory that one would normally gloss over if one read about Landau Fermi liquid theory from, say, modern reviews, for example, by Joe Polchinski or Shankar, which emphasized other aspects of the theory. So let's consider a system of free fermions. So ignoring interaction for a moment. According to Landau, such a system can be described by a Liouville equation that is formulated in terms of the phase space distribution function. F as a function of x and p is the number of fermions occupying the a volume of phase space at point x and at momentum p. So the Liouville equation just look like this. This is basically the same equation that would describe the evolution of a statistical ensemble of classical particles moving in electromagnetic field. So here E and B fields are external fields, external probe that we turn on to measure the response of this system. So here V of P is the velocity of the particles. So V of P is basically x dot, and this is P dot. And this is the Liouville's equations. From this Liouville equation, one can obtain the kinetic equation. From this kinetic equation, one can obtain the linear and nonlinear response. Now, at the time of Landau, actually, I read it was not obvious to Landau that one can describe a quantum system like a degenerate Fermi gas using the same equation that Liouville, Boltzmann, and others used to describe a classical system of particles. And he's taken some effort of a young theorist, a student at the time, Silin, to convince Landau that it was a valid approach. Now, in order to compute the correlation function from this theory, one do the following operation. So here I would illustrate the calculations of the density-density correlation function. One needs to turn on a source that coupled to the density. At that source is A0. So turning on A0, and then we need to compute how much the density changes. And then from this calculation, we extract the value of the density-density correlation function, pi 0, 0. Turning on A0 means that we have an electric field. And all we need to do is to solve the Liouville equation at linear order over this over the deviation from the equilibrium. So this is the linearized Liouville equation, solving it and then putting in the formula for the density. So here I have to solve this equation and say that the density is integral over dp of delta f. Then we find the equation for pi 0, 0, which is written here. Now it turned out that this, yes.
So this is the retarded correlator.
This is a retarded correlator. I epsilon here is written. No, let me see. It depends on how do you, yeah, it is a retarded, written this way. It's retarded propagator. But from the retarded propagator, one can get other type of propagators. Yeah. So here there is this formula turned out to be the same. Exactly, one can reproduce this formula by computing a one loop graph in the field theory of a free fermions. Solving a classical equation, the Boltzmann, this Liouville equation reproduces the loop, the calculation of a loop graph in the limit when Q, but Q has to be small. So Q, absolute value of Q has to be smaller than the Fermi momentum. One can go further, it turned out, and solve the Liouville's equation to order higher than the linear order. And in this way, one can compute the 3-point function, 4-point function, etc. So, for example, one can compute nonlinear response, which we would associate with a three-point function of density by solving the Liouville's equation to quadratic order. Landau also showed how to take into account the interaction between the electrons and go beyond the model, the Sommerfeld model of free fermions. So this modification, Landau argued, has to be parameterized by one single function of two momenta. This function is written here, f of p and p prime. This function enters the energy of a quasi-particle with momentum p. So the energy of the quasi-particle contains the free, the part that doesn't depend on the interaction, and the second part, which basically say that if I have a particle excess or a deficit of particle of momentum p prime, then through this function p, it will influence the energy of the particle with momentum p. So here this is similar to the Hartree-Fock or some kind of a molecular field approximation in statistical mechanics, where the energy of a single particle, it depends on the presence of all particles that surround it. But here, the particle that surrounds it has to be exactly at the same point. If the interaction is short range, but they can have other momentum. So then the kinetic equation is then modified, but it's modified in a way that is very systematic. Basically, we have to treat this as the energy and then define the velocity of the particle as derivative of that object over p, and the derivative of that object over x will also contribute to the change of momentum of this particle.
So sorry, Dan, the reason to take it to be local in position space was the idea that the Coulomb interaction would get screened, etc. Is that right?
That's right.
Okay.
So we have screening at distance that in the metal that's just comparable to the distance between the electrons, and so we have so at distances that is much larger than the screening, and then the modification should be local, but it doesn't have to be local in momentum.
Thank you.
Okay, so now the subsequent history of this subject, this Landau Fermi liquid theory, remains our the cornerstone of one of the cornerstone of condensed matter physics. Using Feynman diagrams, people like Lattinger, Ward in the West, and Abrikosov, Korkov, Zelashinsky in the Soviet Union managed to show that the sum of an infinite number of Feynman diagrams can reproduce exactly consequences of Landau's Fermi liquid theory. So one can hear the statements that Landau Fermi liquid theory can be derived from Feynman diagrams. It's in the sense that it corresponds to a sum of infinite number of Feynman diagrams. Okay, so now let's.
Very sorry to keep interrupting, and Shreya, sorry, just very quickly. So then the idea is that these Landau parameters, Dan, can be derived if you could sum an infinite number of diagrams. Is it these capital
Yes.
Fs?
This capital F turn out to be a sum of some diagram. So it's actually quite subtle how to derive it. To the zero approximation, it is sum of two. So we have to the first object is so-called 2pi diagrams that contribute to the scattering of particle momentum p with p prime to p with p prime, but with a very specific regimes in momentum. So p has to be at the Fermi surface, and then we take the frequency to 0. And it's turn out to be not the whole story. One has to sum this with certain diagram like this, where this block here is not the fermion propagator, but a certain part of the one fermion bubble where some singular contribution taken out. So it takes a couple of chapters in Abrikosov-Kovtelyashinsky to define this. But at the end, this F is just a sum of an infinite number of Feynman diagrams. If one can compute, then we get F exactly. I'm not sure if there is a definition non-perturbative. So that would go beyond the infinite sum of Feynman diagrams, which in principle is just should be a asymptotic series. Yeah, but it might be my ignorance that I don't know that.
I wanted to ask a sort of related question. This F, as you say, seems very closely linked to an S matrix of these quasi-particles. Mm-hmm. But it looks like just the forward limit of this S matrix. Right?
Yeah. Yeah.
So I was wondering why the other parts of the S matrix play no role in the dynamic.
Roughly speaking, it is a phase space that suppress the other. There's no phase space for the other scattering. That's one way to think about that. I think Joe Polchinski emphasized that in his Stasi lecture about Fermi liquid. I think I'm going to explain to you another point of view why exactly this one is it has to be taken into account to leading order, and there is no other elements of the S matrix. But let's see how fast we can go to that.
Thank you.
Yeah. Okay. Landau's Fermi liquid theory can be viewed as the equation describing the dynamics of the shape of the Fermi surface. And the observation here is the following. Imagine that we start the evolution from the initial condition where the Fermi surface is sharp. By a sharp Fermi surface, I mean the Fermi surface distribution function that looks like a theta function, that is F equal to 1 inside some region in phase space and F equal to 0 outside this region. Now, if I subject this system to an external electromagnetic field following the Liouville's equation, one can see that the result at any given time will still be a sharp Fermi surface. The reason is the fact that Liouville's equations conserve phase space. It's an evolution in phase space. And if I follow one particle, then the phase space volume around that particle remains fixed. So if F equal to 1 in the vicinity when it is affected by the flow, the F there remains equal to 1. So if the flow is relatively sufficiently smooth, then the surface that the configuration that we obtain would still can be viewed as a sharp Fermi surface. Now, this Fermi surface the shape and the form, the volume can change from point to point in space. In the beginning, the Fermi surface is round and is the same at any point in X. But as I follow the evolution of this system, this Fermi surface may change shape in X. But view it as one can view it as an evolution in a phase space. We still have a surface of codimension 1 surface in phase space that separates F equal to 0 from F equal to 1. Now, in this sense, we have a dynamic of the shape of the surface in phase space that separate the two regions, F equals 0 and F equals 1. Now, we see here that Landau Fermi liquid theory, at least the way that was formulated originally, is not a field theory. It is based on an equation of motion, a field equation, obeyed by the distribution function or by the shape of the Fermi surface. But it's not a field theory in the sense that where we start with an action and then integrate over all configuration of field. Since it is not a field theory in the textbook sense, we have no access to a large toolbox of effective field theory. We do not have insight from the Wilsonian viewpoint. We do not know how to classify deviation from Fermi liquid theory, how to compute loop contribution. And one of the most important consequences is that we do not know how to couple the theory to a dynamical gauge field to construct a non-Fermi liquid. If we have a field theory of fermions, we can imagine in coupling to the gauge field by just adding a new path integral over the whole field configuration of the gauge field. But since here the fermionic part of the theory is given not as a path integral, but as an equation of motion, Liouville equation, and the other part of the non-Fermi liquid story is the gauge field that is usually described by a field theory. We don't have a good language to describe this hybrid system.
And sorry, Dan, just if one looks at even the diagrammatic definition of the various people you mentioned, that also cannot be extended, is it, in some way to incorporate, say, additional gauge fields, etc.?
I think
say, go ahead, please.
If one is very clever, one probably can do that. So what usually people do is to start not with Landau Fermi liquid theory, but with free fermions, and then couple to that to a gauge field, and then try to operate with it. One of the difficulties with thinking about that field theory in that way is that the low energy limit and the long wavelength limit do not coincide. That is, we can have a quasi-particle with low energy, still have a momentum equal to the Fermi energy. And so we do not have the usual intuition breaks down that way. Also, if we try to do renormalization group, we don't have this notion of a fixed point, because the Fermis, the radius of the Fermi surface also always remains. We cannot get rid of it in the infrared.
I see. Thank you.
Sorry, it seems to me that another issue is that this classical theory only allows you to calculate one kind of correlators, namely retarded correlators. So at quadratic order, as you say, you can just analytically continue between all of them. But at higher order, for instance, if you wanted to compute the time-ordered correlator, just the classical equation, this Landau classical equation, would not be sufficient. Is that right?
I think for 3-point, there is some. I think starting from 4-point function, I think one cannot get the all the correlator out of just the fully retarded Green function. I'm not sure about 3, but you are right that in principle, the field theory should allow you to compute other endpoint function. I have to, yeah, yeah. Although there might be some so roundabout way to compute the spectral density, etc. from the
right. Right. I mean, that roundabout way probably uses the assumption that the equations come from an action.
Yeah.
Right. Once that happens, there should be enough information. Right.
Yeah.
Okay.
So the previous approaches can be divided into 2 subcategories: the fermionic effective field theory, approach, initiated by Benfato Galabotti and then further developed by Shankar and Polchinski in the 1990s. These have the other one that I alluded to. And then there is another class of approaches based on the idea of bosonization by Haldane, Castro, Neto, and Fradkin. Also, I think around maybe late 1990s. These approaches are very elegant in 1+1 dimension. As we know, fermions can be bosonized into boson. And there is it's a procedure that can be done exactly. But in higher dimension, it turned out that the procedure becomes quite inelegant, quite clumsy, and there are one encounters various technical difficulties called patches or curvature of the Fermi surface. And the problem here is that we have an infinite number of bosons. The 1+1D technique seems to be insufficient. Now, in these talks, I'm going to address only a single questions and try to present the answer. Can one formulate Landau's Fermi liquid theory as a field theory with a well-defined action so that the variation of the action with respect to the fields give rise to equations that are equivalent to Landau's kinetic equation? And the answer to this question turn out to be yes, and that relies one can use the method of co-adjoint orbit to construct such an action. I should mention that in one dimension, the method of co-adjoint orbits and the related coherent state method have been applied by Spenta, Gautam, and others. Our work can be thought of as an extension of this method to higher dimension. The main idea is the following. The main idea is that the shape of a Fermi surface, or the shape of a surface dividing f equal to 1 from f equal to 0 in phase space, can be parameterized by a canonical transformation acting on a single particle phase space and acting on the original ground state of a Fermi surface. So any state with a sharp Fermi surface, with a topology of the same topology as the original Fermi surface, same volume, can be obtained from a given reference state by a canonical transformation. So let me just review the mathematics of co-adjoint orbits. Perhaps most of the audience is familiar with this, but just to introduce notations and to see how that can be applicable to the case of a Fermi liquid. So very shortly, if we have a Lie group G and the with the corresponding Lie algebra calligraphic G, then here any elements of the group, I will consider it as an exponent of element of the Lie algebra. And for any Lie algebra, one can define the adjoint representation by commuting the generator that we want to represent it to the generator of the Lie algebra, and by exponentiating this definition of the adjoint representation, we can define the adjoint representation of the group also on the acting on the Lie algebra. Any Lie algebra and Lie group has a adjoint representation. And to define the co-adjoint representation, I have to introduce the dual space, and I'm going to define the co-adjoint representation as a representation acting on the dual space, so that it preserves the scalar product. So this is my convention for the co-adjoint representation. So a co-adjoint orbit is the orbit of a given vector in the dual space when one acts on that with all possible elements of the Lie group. So the co-adjoint orbit can be thought of as a coset of the Lie group and the group of all the elements of that Lie group that leaves the given chosen F0 elements of the dual space invariants, coset of the Lie group and the stabilizer group H. So the simplest example would be a SO2 group where the co-adjoint orbit, both the Lie algebra and the dual space are three-dimensional space R3, and the co-adjoint orbit is just a sphere. Now let's go to the group that is our basis for the constructing of the co-adjoint orbit, the group of canonical transformation. So by canonical transformation here, I have in mind canonical transformation acting in the phase space of one particle. So that phase space is X and P, and the dimension of X and P is X has D dimension and P is D dimension. And a lot of time I'm going to stick with two-dimensional space and two-dimensional momentum space. But a lot of formula will be valid for general dimension. In an infinitesimal canonical transformation is generated by a function in phase space in this way. X goes to X prime equal X minus epsilon gradient of PF, and similar equation for P. You recognize here the time evolution of a particle under the action of a Hamiltonian F during a time that is equal to epsilon, which is small. A time evolution preserved Poisson bracket. So this is infinitesimal canonical transformation. The Lie algebra of this canonical transformation is given by the commutator in this Lie algebra is given by the Poisson bracket. That is the commutator of two of these infinitesimal canonical transformation with parameter F and G is another canonical transformation, infinitesimal canonical transformation with parameter given by the Poisson bracket of F and G. F and G are both function in phase space. Now, knowing the Lie algebra, one can construct the Lie group of canonical transformation. Now, these would be finite canonical transformations, which can be visualized as, again, a time evolution following equation similar to that, but except that we exponentiate it and make it into a time evolution during a unit time instead of an infinitesimal time. So that would be given by the exponents of an element of the algebra F, where F can be represented as a function in X and P. Now, we can also define the notion of a dual space that is a space of all, again, the all function of X and P. And I'm going to define the scalar product of elements of the dual space to the element of the Lie algebra simply as an integral over X and P. This is a simplest convention on the definition of the scalar product. Until now, things seems to be quite formal, but going ahead, it is good to have in mind the following physical interpretation of different mathematical objects that has appeared. The element of the Lie algebra F are going to be associated with physical observable. For example, F equal P square over 2m is going to be associated with the kinetic energy of a system of non-relativistic fermion. So these are observables that are restricted to single particles, since they are single particle observables, like the sum of all the kinetic energy of the particle, or sum of all potential energy of this particle, or the moment of inertia of the system. They are all parameterized they can be put in correspondence with a generator of the Lie algebra. The small f, the member of the dual space, is going to be associated with a state of the system. This f is the distribution function of the system, and the scalar product between small f and big F can be thought of as the average expectation value of the physical quantity f over a state given by the distribution function f. So this can be written as an expectation, can be thought of as an expectation of f in a state that is given by f. And the quantum mechanical analogy is the trace of rho f. Here the f here is in quantum mechanics should be replaced by the density matrix rho. Integral over the phase space will be replaced by the trace. Now the adjoint and co-adjoint group action of the group of canonical transformation can be also obtained. And here it turns out that they look at the level of the formula is exactly the same. That if one act element exponent of G on an element of the Lie algebra F, we would have to add to F the commutator and then the double commutator, etc., in the form that has a coefficient exactly like a Taylor expansion of an exponent. One can check that these actions preserve the scalar product. If the scalar product is defined as integral over phase space of the product of two functions, then so if I define this the x dp f x in p f x in p, then this adjoint co-adjoint group action preserve the scalar product. Okay, so now I'm going to use this to parameterize my state of a fermionic system, which is given by arbitrary shape of a region in momentum space. So here I'm thinking of a two-dimensional momentum space, px and py, and at any given point x, the system would have a Fermi surface, but the Fermi surface shape can change from point to point. Such a configuration, I claim, can be obtained by acting on a reference configuration F0 by an element of the group of canonical transformation. Now, canonical transformation, by definition, cannot change the distribution function. It has to preserve the condition that f is equal to 1 or f equal to 0. Since a canonical transformation is basically a Hamiltonian evolution with a given Hamiltonian over unit time, that sharpness of the Fermi surface should preserve. And so here we have a way to parameterize the Fermi surface as a point on the coadjoint orbit of the group of canonical transformation. So it turned out that this is a very convenient choice of parameterization, much better than other choice. One may be tempted to parameterize the shape of the Fermi surface by the height function, how much it deviates from the round shape. But it turned out that the formulas, but it's very difficult to write down a general formula for the action. So let's work out how the shape of the Fermi surface changes under an infinitesimal canonical transformation. A canonical transformation close to unity. So the group element is parameterized by an exponent of a group of an element of the Lie algebra, while that phi is very small. And then the distribution function is going to be to linear order in phi is given by the original distribution function plus the commutator of phi with f0, sorry, the Poisson brackets of 5 f0. And after calculation, one actually see that this remains the Fermi surface as expected, remains sharp, but it shifted away at each point in momentum space by an amount equal to this thing. So it's a gradient of phi over x along the direction of p. There is actually an ambiguity. We have mentioned many different elements of the Lie group correspond to the same, would move f0 to the same point. So the two elements of the group u and u should be considered as equivalent. If it's if the second element is the products on the right by a element of the stabilizer group, and using that one can do a gauge fixing. Instead of having a function of x and p, one can, for example, choose the function to be a function of x and theta. So phi does not now depends on the absolute value of p. The general phi would be a function of x, the absolute value of p, and the direction of p. But here, after gauge fixing, it's a function of only x and theta.
Right.
So here,
can I think of the stabilizer group as in some sense a Cartan subalgebra of this group of canonical transformations? In the Lie group story, that's the stabilizer group was the Cartan subalgebra, right?
But here, I think this subalgebra depends on the initial distribution function that we have.
Yeah.
So, roughly speaking, these are these transformation that does not change the shape of the Fermi surface. So I'm not sure.
I think that was the case even in the Lie group story, right? You take some guy, the things that don't change it are the stabilizer, but you can always move that guy to be diagonal. You can always rotate that guy to be diagonal, and then the guys that don't change it are just the Cartan subalgebra. So
this guy is not an element of the Lie group. That's I'm not sure in which sense it's diagonal. This guy is just some elements of the dual space, which I have to think about this. But
it's not important. Thank you.
Yeah, I'm not completely sure if I can identify it with the Cartan subgroup. And so here, what we see here is at this moment, after all this mathematics, we see something that's quite physical appearing, that we have after the gauge fixing, the degrees of freedom in the theory is an infinite number of scalar field. Basically, you have one scalar field per point. At each point on the Fermi surface, we have a scalar field. So that is mathematical manifestation of the statement that the field theory of Landau Fermi liquid should be a theory of infinite number of fields. So here we have one field per point. On each point there is a field, scalar field.
Damn, sorry. Is there a way to understand this stabilizer geometrically, let's say, for any given state?
Understand? I mean,
well, a priori, is there a reason to see that this is what I should have? Sorry, it's not a very well phrased question, but this is what the stabilizer should have been, or is there a way to kind of I'm not sure. But is there a way to expect this answer? Is there a way to be sure that okay, this makes sense, or this is?
I mean, is there a way to?
It's fine. I mean, if it comes out of the calculation, I can see that. But let's say if there was a different shape to begin with, could you say what this would be, or that would also be an involved answer which would come out after doing this analysis?
If the shape is topologically the same as a disk, then the answer would be the same, because these would belong to the same coadjoint orbit of a disk. So
I see. So this is only topological.
Yeah, it depends on the topology of the coadjoint orbit. They are classified by the topology of the initial Fermi surface and the total volume. So that's the only thing.
I see. So all the distributions that are topologically connected would be reached by this operation.
Yes.
I see. Okay.
Yeah.
Sorry, just one more question following up on Abhijit's question. In a Lie algebra, your various coadjoint orbits would be labeled by eigenvectors, one for each Cartan element. Right? You diagonalize your Lie algebra element, and then in each diagonal element you have one discrete number to specify that specifies your coadjoint orbit. So there seems like a lot of data specifying which coadjoint orbit you're looking at, and this maps to the various representations of the Lie group. Right? The various irreducible representations of the Lie group are basically in one-to-one correspondence with the allowed coadjoint orbits. I was wondering why there was so little information going into specifying your coadjoint orbit here, which seemed to be specified just by total number of states, just one number.
Total number of particles. So the total number of particles commute with all the other Lie algebra elements. So what I can say is that I at least in the vicinity of a circle, I can show that any deformation can be reached by elements of the Lie group. But I think anything, but from that, I think anything that is connected to the spherical, to the disk, to a round disk, can be reached by a canonical transformation.
Okay, so let me make a suggestion. I mean, in the Lie algebra situation, there are special coadjoint orbits where you turn on only one non-zero eigenvalue and everything else is zero. Those orbits would be specified by just one integer. So perhaps this is the analog of that. And perhaps if you have 2 disks or 3 disks or 4 disks or 5 disks, then that's turning on more and more eigenvalues. I mean, this is very weird. I'm sorry.
Yeah, I don't completely understand all this representation of the canonical transformation. There is another type of coadjoint orbit when we just start with the point in phase space, it's just a single particle, which is a point x and p, and then in acting on it, we can move this point around, and that's also be a completely different type of coadjoint orbit. So that we want to describe the motion of a single particle. That would be the coadjoint orbit that one needs, and it seems to be so I haven't thought very deeply about it.
Can I make a comment?
Yeah.
Hi, Dan. This is Gautam.
Hi, Gautam.
Yeah. So I, indeed, as far as I remember, that in the case of the LLM geometries also, where similar things appear, or even in the case of the C = 1 Fermi fluid that we had looked at, disconnected droplets do appear quite easily if you start from the quantum theory, because if you take out an electron from somewhere in the middle of the Fermi C and take it up somewhere, then that starts a new coadjoint orbit. Of course, you have to take a number of electrons together in order to make a sort of classical annulus up there. And then the most generic configuration would have a whole number of, an infinite number of possibly disconnected droplets in the n going to infinity limit. And they will all be, the starting point of their own coadjoint orbit. So these could correspond to the various Casimirs that Shiraz is thinking of. Because the area of each of these droplets would be preserved. That's what I was saying. So there will be infinite number of numbers specifying those coadjoint orbits, and these things do appear in the context of the LLM droplets.
Okay.
So, sorry, Dan, I know you have to go on, and there's been a lot of discussion, but just to understand the final bottom line on this slide, physically, is the point that if you look at the distribution function f, we don't want to allow changes in the normal component of the momentum, because that changes the energy too much of the Fermi surface. So we only allow changes along orthogonal to the normal.
We allowed change. We allowed any change that is smooth of the Fermi surface. So, for example, if this is the original Fermi surface, we in principle can make it move like that. What I was trying to draw is that a stabilizer group is the one that doesn't change anything. A stabilizer group is the type of canonical transformation that can only change point parallel or to the Fermi surface.
Okay. But then why is the final set of degrees of freedom a boson which has x and only theta? I'm sorry, I didn't understand that well enough. The angle was the only physical thing the boson depended on, right?
Yeah.
Sorry
basically, anything that this boson does in the middle doesn't do much to we don't physically we don't need to know how this canonical transformation acts inside or outside the Fermi surface. We only need to know how the canonical transformation moves the Fermi surface itself.
Okay.
That's how, at the end, we only need to know a function of x and theta, not x and p. If p is very small, much smaller than the yes. Yeah, roughly speaking.
Yeah. Sorry, please go ahead. Yeah.
Yeah. In this, well, maybe I stopped that. That's how it works.
Okay. Thank you.
Can I ask something about this gauge fixing, which I'm trying to understand? Suppose that the Fermi surface has a fold, so that the one radial line cuts the boundary in not in 1 point but 3 points. Suppose it has a fold. So then this gauge fixing, will that still work?
I don't know. Here we limit ourselves to very small infinitesimal change in the shape of the Fermi surface. If we have a fold, then we have to parameterize it differently. And actually, I don't know what is there a gauge fixing that can be continue to such kind of transformation. Ideally, I don't know how to gauge fix.
I mean, in one plus one dimension also this problem appeared, this problem of the gauge fixing. So we had to go to the parameterizing the boundary of the Fermi fluid in terms of some intrinsic parameterization of the fluid boundary itself. So not by using the coordinates given by the phase space, but by intrinsically parameterizing the boundary of the Fermi fluid, which of course had no problem, because that parameter always went from 0 to 2 pi or whatever it is. So it required a bit of jugglery using that. So here I would have thought that a similar procedure would also handle folds in which you parameterize the boundary of the Fermi fluid itself, in terms of maybe 3 parameters. So it's kind of a world sheet.
Yeah, that is an interesting. We don't have as I'll show you some formula. We don't have the expression for the action expressed in terms of this surface, this coordinate on the surface yet, though they should exist, but I don't have the formulas yet.
Yeah, maybe I can offline. I can tell you a bit how we handled this fold business recently in some the condensed matter context. I'll tell you later.
Yeah, thank you. Okay, so I will show you the action, and then maybe mention some consequences. So this action turn out to be the sum of the 2 parts. So this part, the Hamiltonian, is the easiest part. It's the part where that part can be thought of as the total energy of a system with a given shape of the Fermi surface. For example, in the case of a free particle, that is simply the sum of energy of all particles inside the Fermi surface, or in the formal notation would be the scalar product of the kinetic energy with the distribution function. The first term is the Westermann-Witten term plays the role of the PQ dot term. So while this is the Hamiltonian, in order to specify the total action, we need the Berry phase term, or the term that give rise that correspond to the symplectic structure on the phase space, and that is given by this formula. There are another way to write this action. It is an integral over Kirillov-Kostant Souriau symplectic 2 form over a 2-dimensional surface bounded by the trajectory of our system in time. So here you see this U is the elements that translate F0 to F by U. U minus 1 dtu is the element of the Lie algebra. And we can always construct the scalar product of F0 with the algebra. And one can show that these 2 forms of the action are the same. And in the first form, the action changes only by a total derivative, where we replace U by U times V, where the V is the elements of the stabilizer group.
So just to make sure, this is the action which produces the Liouville equation of motion.
Yeah.
Is that okay?
If you vary this action with respect to possible changes in F, you find the Liouville's equation.
Thanks.
Yeah. So let me show you one at the quadratic level, how it looks like. If I expand over phi to quadratic level, we would find an action of an infinite number of bosons, chiral bosons. Each boson move in only one direction in space, a direction of p, and they are not interacting with each other. And from this quadratic action, one can compute, for example, the current correlation function. But one can go further in.
I'm so sorry, I missed the connection between U and phi.
So the an element of the algebra is a function of x and p, or I choose it the gauge so that it's a function of x and.
Okay, thank you.
U is exponents of that. It's a element of the Lie algebra that one get by exponentiating this f.
Okay, thank you.
So U is the sum 1f, f squared, etc., and that one can go to cubic order and then write the action. So boson is different theta now at cubic order would couple to each other. So that was actually something that not very clear to people who were doing bosonization in higher dimension in the 1990s. They can easily guess the form of the quadratic action and give an argument that such an action should arise if one bosonizes the system. But going to the cubic order, one think only using the co-adjoint orbit method, one has a systematic way to go to include the interaction between the boson at different points. Now let me show you how to include the Landau parameter. Turn out that the Landau parameter in so the Landau parameter turn out to be a term in the actions that can be written as integral over d theta prime of let me write. Yeah.
Just one question. How do we know that this is the right action? I mean, it produces the right equation of motion, but
how do we
taking this action and writing down higher order interactions, etc. We know that that this is the right action for that.
What is so the question is so for free fermions we can derive this this action from a coherent state formalism. Maybe I mention it a little bit later. But it should be a right action because basically from physical consideration, first of all, the action must contain the information about the total energy of the system, and then after that, the time with first derivative in time is uniquely fixed. There is only one thing that one can write out. Is Kirillov form. Is it? Does it answer your question? I'm not sure what you are looking for.
I mean, there are probably multiple terms I can write, right? So, what sort of symmetry considerations I should have while writing this down and say that okay, with respect to these symmetries, this is the most general thing, and then I'm. So, what are these considerations?
So the action, so to leading order, we want to write down an action with the smallest number of derivatives.
Okay.
Yeah. So
so there could be corrections to this also.
Yeah.
And those are subleading in some sense.
Yes. So it turned out that the only terms that one can add to this action is the Landau interaction. which doesn't have an extra derivatives. So the Landau interaction is basically terms that look something like this, phi and then n theta prime that x of phi. N is a unit vector along the theta direction. So this term has the same number of derivative as the kinetic term. So the term that was before was like d theta n pi square. And there is some coefficient here, but the coefficient can be a function of theta prime. What is special about this term is that it has the same number of derivatives, and it has, I didn't mention, but there is a residual gauge transform. There is a residual gauge invariance. Even so, after gauge fixing, we still have a residual gauge invariance, and this is the only term quadratic, and the only term with the same number of derivative is the term that appear in free theory that is invariant under the residual gauge transformation. So in some sense here we can derive Landau's Fermi liquid theory by just looking at the action and then ask what terms that are not suppressed by derivative that we can add to the action of a free theory, and Landau term is the only one. In bosonized language, actually, Landau term interaction is not an interaction term, but just a quadratic term. It's just a modification of the quadratic Lagrangian. That's yeah.
Thank you.
Yeah, sorry, I have some similar concern to Abhijit's thing. Yeah. The way I understand the kinetic term is that is for the free fermions, you had basically the non-relativistic, fermion kinetic energy, which is like, psi dagger I del T psi. And then psi dagger, so in case of free fermions, psi just transforms, as you say, by U psi to U psi, where by the psi, I now mean the second quantized fermion field. So psi goes to U psi and psi dagger goes to psi dagger, U dagger. So you have U dagger, U dot kind of structure coming in, which you have said here. And the psi dagger and psi which sit outside, they correspond to a particular, starting element of the group and so on. But the point is that in case of interacting theories, can I think of psi going to U psi as a general parameterization of the second quantized Fermi field? Because I would expect that it would go to psi, should go to psi plus, psi, psi dagger, psi, things like that. I mean,
we don't have a derivation of this theory this theory in the case of interacting fermions. So we don't have a microscopic derivation. So the sharp Fermi surface in Landau theory is not a Fermi surface of the original particles. It is the Fermi surface of the quasi-particles. So whatever at psi, psi dagger, psi, here should be a field of quasi-particles. So here my guess is that what we have here is a class of possible effective field theories that we have to write down and postulate the symmetries. And after that, basically here we postulate, we make the following postulates that the Landau, that Fermi liquids are described by the degrees of freedom that are the shape of the Fermi surface, right? And we have to write down an action that depends on the trajectory of the shape of the Fermi surface in time, and this would be the first term would be correspond. The first term in the action would correspond to free fermion plus Landau interaction. And then whatever the symmetry allows in the interaction term should be there.
I see. So this kernel capital F, these Landau parameters, they would not enter the kinetic term, right? That's
no, it's actually in the bosonized language. The kinetic term would look something like this. So there is a phi dot term, and then there is kinetic term of the free particle. But then this one is a quadratic in phi. So in order to find the propagator of phi, we have to diagonalize the whole things, including the Landau interaction. So that is what interesting about this, about the bosonic viewpoint. Landau parameter is not Landau interaction is not interaction at all. It is the modification of the kinetic term, which is non-local in momentum, but it's local in space.
I see. This is nice, isn't it? But the time derivative does not get, the time derivative term does not get modified. This does not get the kernel capital F.
It seems to be rigid, at least.
I see. This part is not clear to me, but maybe we can discuss this. Yeah.
This part, I think I can only show that the correction to this phi dot. There's no corrections that are of the same. They have the same number of derivatives as the leading term that one would write down. Maybe in higher derivatives term, one has some freedom.
I see.
Yeah, there is no similar freedom as in the Landau interaction.
Okay, thank you.
So, okay, so maybe I can conclude soon. Let me show you some possible extension of this, of our approach. We can think about the algebra of canonical transformation as the long wavelength limit of the algebra of fermionic bilinear, psi-Decker-psi. Psi-Decker-psi, where psi-Decker-x, psi-y form a closed Lie algebra. And if we do a Wigner transform, we can show that the commutation relation is given by a Moyal bracket. And in the long wavelength limit, the Moyal bracket becomes the Poisson bracket. And that's how the algebra of canonical transformation appears. That suggests a way to extend the theory to spinful Fermi surface. In addition to psi-Decker-psi, we have to include operators that involve spin, sigma A, and how to extend the theory to include superconductivity. In addition to psi-Decker-psi, we have to include psi-psi and psi-Decker operators. So these are the things that we would like to do. So let me conclude. The method of coadjoint orbit provides a natural way to write down an effective field theory of a Fermi liquid. The result of this procedure is the bosonization that works also at the nonlinear order. It produces linear and nonlinear responses of a Fermi liquid, and perhaps it might be a suitable starting point for the study of non-Fermi liquid. Thank you very much.
Thanks, Sam, for a wonderful talk. Let's see if there were quite a few questions, but let's see if there are more questions from the audience.
I thought the talk was totally fantastic. Thank you so very much. I have one very vague and sort of speculative question, which is this: that the way you presented it was that you started with an equation of motion, and then you beautifully used the symmetric considerations to obtain an action which reproduced that equation of motion. Now, as you know, there's another system in physics where the easiest thing to write down is an equation of motion, namely the equations of hydrodynamics. And people have been working hard recently to try to produce actions that would reproduce those hydrodynamic equations of motion. You know, Mukund Rangamani, Loganayagam, Hong Liu, and various other people. I was wondering whether there was any similarity between what they're doing and what you're doing. It's a very vague question. But
okay, so I can tell you that we started, I think, there was a book by Arnon and Hessin called, maybe you know it. Hamiltonian, I forget, some kind of method in hydrodynamics. Umang was studying it for a reason that I forgot. Probably it's also related to trying to formulate hydrodynamics with in terms of the action. But at the end, it's the we deviated to Fermi liquids and.
Oh, okay.
Yeah,
Okay.
but I think it's I think there is some similarity, but I'm not sure which kind of group I should start with. Let's see. So I think there might be a suitable choice of a group can produce a state. One would be tempted to identify the group of diffeomorphism as the group that will generate given hydrodynamical configuration, but it seems to be not sufficient. If I have the group of canonical, it might be a different group. So I think there's probably a way to formulate dissipation-less limit of Navier-Stokes, that is the Euler equation, might be possible to formulate as in terms of the coadjoint orbit action of some sort. Yeah.
Thank you very much.
So sorry, can I ask a question?
Go ahead, Sandeep.
Okay. Yeah, no, thank you for a very beautiful talk, Dan. Sorry, I've got a very remedial question. So if I understand then that the effective field theory has these Landau parameters as just additional coefficients or coupling constants sort of in the theory, right? As important as the leading kinetic energy.
Yes.
And so in that sense, then it's not a very predictive theory, right? Or is it that given all the Landau parameters as an input, we then predict a lot of things? I mean, I'm just asking, how powerful is the effective theory?
So it's in practice, well, let's say, in practice, maybe let me try to and then think on the way. In practice, for helium-3, only a few first moment angle in the harmonic expansion of the function f is important. So this function depends on the two angles. On the angle between two vectors, so it can be expanded into into harmonics, and only the 0 to 1 and maybe the f2 is differ from 0 appreciably.
Okay.
Yeah, and I think one can get measurements of several things. So let me give you just one thing. F0, so the isotropic part of the function f is related to compressibility. So one can measure that F0 easily. F1 is related to the is fixed by Galilean invariance and the effective mass. So measuring the effective mass of the particle, which can be done through specific heat, one get the first component F1. If one assumes that F2 is 0, one get a prediction for the speed of the zero sum. And I think that's pretty much already quite well with experiments, since F2 is not that different from 0. So yeah, but I think there could be more. If one may, in principle, here you see there is an infinite number of parameter in principle, but it predicts an infinite number of output, which is the 2-point function as a function of omega over q, or the 3-point function as a function of all possible ratio of and orientation of particles. So it's actually a predictive theory.
I see. Okay. Thank you. Thank you very much.
Well,
yeah, can I ask a question about bosons? You know, the nice thing about the fermions is that the phase space distribution is just governed by the boundary only. On the other hand, in case of a Bose phase space distribution, the height is not one uniformly everywhere. So that's another. So there is probably, I'm just wondering whether there is any kind of nice phase space formulation like the one you presented, for Bose liquids.
In the case of fermions, it's simple only at 0 temperature. For boson at 0 temperature is usually a simpler system, unless some kind of large n or there's some problem. But a single boson with repulsive interaction becomes superfluid, and there is only one Nambu-Goldstone boson in the infrared, so the description is much simpler.
That's about the ground state. Yes, that's 0 temperature. Yeah. But generally, the configuration space of bosonic states would be. I can imagine that it can be described by phase space distribution, but something which is not just 1 or 0. Therefore, something. I see what you mean. Of course, for the ground state, yes.
In the case of fermions, it's also this. One would encounter the same problem if one tries
with the finite temperature.
Finite temperature. I think one can try to extend the notion of co-adjoint orbit there, so the stabilizer group becomes smaller. If I fix, for example, Fermi-Dirac distribution function and try to go from there, we have a smaller stabilizer group, and perhaps one get. I think one at the end probably would be able to get some kind of revealed type of equation.
I see. Can that be done?
It can be done, but I'm not sure how useful that would be, because we know that at finite temperatures, collisions between particles, dissipative effect, etc., becomes important. So I don't know if this will. It's probably not a full description. Full description probably would require some double contour.
I see what you mean.
Thank you.
Okay, thank you.
Okay, if there are no further questions, let's thank Tam again for a wonderful